Good afternoon, everybody, even if here it's still in the morning. And I would like to thank Lisa for the invitation. I'm happy to be here today to talk about the fluid path in subduction zones, particularly what we get from using boron isotopes in serpentinites. So subduction zones are very interesting because they are the main interface on Earth for chemical exchange between the surface, which is going down as the slab, and the mantle wedge. And all these exchange are happening through fluid exchange mostly. And if we know quite well what's going in, it's the oceanic crust plus a little bit of the mantle or serpentinites underneath. And we go pretty well what's going out. It's when we study the arc volcanoes. Well, we still have question about what happens in between. And serpentinites are actually a very good tool to study what happens in between fluid-wise because they contain up to 40% mass of water, which is huge. And we can find them everywhere in subduction zone. And on the top of it, they are enriched in boron. So here on that side of the screen, you have 3 examples of serpentinites showing how heterogeneous they can be and how diverse they can be. And when I say they are ubiquitous in subduction zones, well, it means that not only they are available as seafloor serpentinites or abyssal serpentinites, that are the serpentinite in the oceanic crust that are going to enter into subduction, but in the subduction cells, we can also find them as number 2 here in the slab, so-called slab serpentinites. We have all the serpentinites forming above the subduction channel in the mantle wedge, called number 3 here. And finally, we have the 4-arc/ophiolite serpentinites that are much closer to the surface. And so I would say in the past, before we developed the in situ method to look at all these serpentinites, well, the abyssal serpentinites were pretty well documented because there is all this IODP drilling and dredging the seafloor. So we could have a decent amount of analysis on them. All the other kind of serpentinites, I would say, were poorly analyzed. There was one study on the 4-arc serpentinite, one on the so-called mantle wedge serpentinite, and a couple of data on ophiolite. For ophiolite, there was no boron content. So in this delta 11 boron versus boron content, we could only report like the minimum and maximum isotopic measurements. So since we developed the in situ method here in New York, well, we have increased a little bit the number of slab measurement in the top in blue, but most importantly, I would say we have discovered, we have identified all these negative boron isotopic signature that has never been really seen before, and that are mostly found in mantle wedge serpentinites. Also, we have significantly increased the number of subduction zone ophiolite, all this data in purple here, and they match pretty well what was published before. Also, as we can see on the mantle wedge serpentinites, we have seen serpentinites that have very high boron content, here up to 200 ppm, but we have even higher content than that in some samples. And so the results I'm going to present today have been collected in serpentinites somewhat worldwide. We have samples from Canada, Nicaragua, Guatemala, Ecuador, Brazil, Corsica, the Alps, and Iran. So I think we can say that it's not a single subduction zone that has this behavior, but the samples we have, the results we have are somewhat global. And so I will explain why do we use boron and what's the impact of this element on serpentinite study. Then I will present tectonic setting versus fluid origin, because most of the publication presents the tectonic setting in which serpentinization happened, while we should really talk in terms of the fluid that was responsible for serpentinization. And a very important point, if I have the time, talk about development of standards for in situ analysis. So why do we use boron? Well, because boron is concentrated in the serpentinites between 2 and 800 ppm. That makes it relatively easy to measure. And most importantly, it's literally absent from the ultramafic precursor, less than 0.1 ppm. So which means that all the boron we measure in our serpentinites is coming from the fluid or the fluids responsible for serpentinization. And that's very important in comparison to some other stable isotopes, but that are major, like oxygen, for which we already had a significant amount of oxygen in the rock prior to the event. So that's a great advantage of boron. The other one is that boron is a light fluid mobile element. So it means it fractionates easily in function of the temperature, the mineralogy, the pH. And fluid mobile means it will be traveling easily in the fluids, and it will partition easily into the fluid phase, whatever is aqueous or melt. And surprisingly, I would say the heaviest isotope, boron 11, is more compatible in fluid phase than the light isotope. And so when we have fluid rock interaction, we really have significant fractionation that we can measure and interpret. So the in situ method I was talking about, so we developed that a little bit more than 10 years ago now. So we couple a laser, an excimer laser with a multi-collector Neptune. We did everything here at Clermont Doherty Earth Observatory, Columbia University. And we compared our analysis with SIMS measurement, which is the traditional in situ method for boron analysis. And so it's what you see here on the graphic. You have the SIMS measurement that are the little stars, and the other, the diamond and the triangle that are laser ablation coupled with the multi-collector in different kind of samples, in minerals, I should say, in micas, in pyroxene, and in serpentine. And so we overall have a good agreement of the two methods, with a big advantage of the laser ablation being like one analysis takes more or less 3 minutes, while when I was going to Woodsall to do the SIMS method, it was half an hour. So we are 10 times faster, which allowed to multiply the data in comparison to the SIM. And all the results here are presenting as delta 11 boron, which is, I'm sure you're all familiar with that, the comparison of the isotopic ratio in a standard with the sample we measured, multiplied by 1,000. And so now that we have a method to analyze all these serpentinites, well, we will see what I mean by tectonic versus fluid source. So very often when you read paper related to serpentine in subduction zones, well, it's actually how it's called, subduction of serpentinites. And as we see on the graphic on the top, well, it can be more or less everything. It can be slab serpentinite, it can be mantle wedge serpentinite, or forarc, or even ophiolite. And if we look at the delta 11 boron of these subduction zone serpentinites, well, it varies from -18 to +35. So basically, it covers the entire range possible of delta 11 boron value in serpentinites. So that's not very informative, and that doesn't really help us. Another problem, I would say, when you try to detangle what's happening in terms of serpentinization related to subduction zone, it's the ophiolite, or the so-called ophiolite. Very often, as soon as there is serpentinites found on land, in mountains, suture, etc., it's called ophiolite. And ophiolite has a definition, kind of a straight definition, which is mid-ocean ridge material that is trapped during the closure of ocean basin. And even more recently, there was a subdivision of suprasubduction zones of ophiolite that are likely ancient forarc lithospheres that are also abducted. In both cases, whatever it's the general definition of the supra-subduction zones of your light, nowhere the definition assumes that the serpentinites are subducted. And there is plenty of publication where they call meta-ophiolite or subducted ophiolite, and that makes that really difficult to identify what is what. So that's, for me, one of the problems to talk in terms of tectonic settings versus fluid origin. And what we know for sure in terms of both tectonic setting and fluid, it's the seafloor. Because, well, as you can see on the upper figure, serpentinization occurs in the seafloor with little cracks or fracture or whatever. The seawater is percolating through the oceanic crust and underneath to the lithospherate mantle and serpentinize it. So we know for sure that the abyssal serpentinites or the seafloor serpentinites have been serpentinized from seawater or seawater-derived fluid. Thankfully, the seawater has a constant delta 11 boron around 40 per mil, and consequently, the seawater-derived serpentinites have a delta 11 boron in the range 5 to 20, as we can see on the diagram on the left. So that, I would say, is our anchor for what is seawater-derived fluid. Then, if we look at mantle wedge, so that would be number 3 in the subduction sketch, well, we thankfully had that very interesting outcrop in Guatemala when we have in contact high pressure rocks like eclogite or tribolite, serpentinites, which is hydrated peridotite, obviously, and jadeite or mica rocks that represent veins. So it's directly kind of a snapshot of what was the composition of the fluid. And so we were able to measure boron isotopes on mostly the veins, I would say, and the serpentinite. And what we saw is that they have very negative value. So it's quite known that the subducted crust, I would say, the top of the slab with metasediments, so metabasalts and metasediments, are getting more and more negative when you go at greater depth, because the boron 11 leaves more easily than the boron 10. So that's relatively well known, but it has never been really observed or interpreted in serpentinites. And so in 2 subduction zones in Guatemala and one from Nicaragua, well, we clearly see that the serpentinites in contact with these subduction zones fluid are very, very negative, down to -80. So we interpret this negative value as being serpentinites coming from subducted crust-derived metamorphic fluid. So it's a little bit cumbersome name, but it really means it's the fluid derived from the metabasalts and metasediments. And so we can see that they are basically all below +10 per mil. Another well-constrained area is true slabs. So we have a bunch of samples from Corsica as well from the Alps, even if these samples are sometimes called meta-ophiolites. I think everybody agrees that Montviso is an actual piece of slab subducted. And so when we analyze these samples, well, they are all above 10 per mil and very similar to the modern oceanic seafloor serpentinites. That is the little C here on that figure. So that means in the slab, we still have the signature of seawater-derived fluid with serpentinites above 10 per mil. So we drag down the boron isotopic signature down to the level where the serpentinite is not stable anymore. And this here is in good agreement with abyssal serpentinites. Another example is called ocean continent transition ophiolite. So that would be the, I would say, true definition of an ophiolite, a piece of oceanic crust which is abducted at some point into the continent. This is absolutely not related to subduction, as ocean-continent transition are in passive margins. And we can see that in this case, again, in these samples from Brazil, we mostly have a positive signature above +10 per mil, meaning this is seawater-derived fluid. And okay, so yeah, to conclude, I would say this chapter. So we can put in this big delta 11 boron versus boron concentration diagram, we can put all the serpentinites we measure in different areas, and we clearly see that the one that have seawater derived signature are all above +10 per mil, rather than the one that have a signature derived from like the subducted crust and subducted sediments have a value below +10 per mil. So we really have that threshold, I would say, at +10 per mil that allow to interpret much better rather than just, hey, that's subduction zone serpentinites. Yeah, well, we have some for which the fluid is indeed coming from the subduction, and we have another half above 10 per mil for which seawater was responsible for serpentinization. And so, interestingly, if we now look at the true suprasubduction zones of ophiolite, so which is what we encounter the most, I would say, in terms of ophiolite in mountains. Well, interestingly, on these data, both the one we acquired in situ that are in purple and the one that have been acquired in woodwork that are in white, well, we can see that they overall straddle that 10 per mil threshold. So with most of them being between +10 and -10. So that's somewhat different from seawater only or subduction fluid only. And so we interpret that as being a mixture of both seawater and subducted crust derived fluid. And that fits very well with the idea of this happened in 4 arcs, because 4 arcs, you are just at the beginning of the subduction. So you still, when the slab is bending, you can have seawater coming in, and you have the very first dehydration related to subduction. So you have both fluids that can mix in the area of formation of these suprasubduction zones of your light. So what we have been able to define these past years, it's that in terms of subduction zones related serpentinites, if your serpentinites form from seawater, the delta 11 boron is going to be above 10 per mil. If your serpentinites with subducted crust derived fluid, delta 11 boron is going to be below 10 per mil. And if you are looking at suprasubduction zones of your light and probably also 4 arc serpentinite, you are going to have a mixing of both fluid, both seawater and subducted crust derived. So I don't really have time today to present like application of this, but this has helped us tremendously to kind of detangle what kind of fluid are responsible of what event in the serpentinite, particularly when you see that some serpentinites can have 2 or 3 successive events of serpentinization, sometimes with very different fluids. Some couple of papers are now under review or already published. Another aspect I would like to talk about here is development of standards, because people who are doing SIMS or every kind of in situ analysis knows that usually we need a matrix matching standard for this analysis. Unfortunately, all these analyses, I would say, have been done without a good matrix matching standards. And so just because there is no serpentinite standard for in situ boron analysis. so far, whatever it's by seeds or by laser ablation. So more or less each lab doing that as their in-house standard, that is more or less good. Unfortunately, often less than more. And what's the big problem is that a great matrix effect is assumed, at least for SIMS measurement, up to 6 per mil. That could shift significantly all our results. And the only serpentinite standard that has been analyzed for boron isotope as a bulwark is UBN, which is an ophiolite serpentinite. And it has been analyzed twice, but there is no certified value of it. And the big issue is a powder. So that doesn't make it easy to analyze. So I tried to make pressed pellet with this powder and analyze it by laser ablation. So what we can see immediately is that it's terribly unstable. Both the analyses themselves, the error bar are huge. It varies, you can see on that diagram, from -15 per mil to +30 per mil. So it's really not great. And even individually, we have a lot of fluctuation as the 2 sigma is 13 per mil, which is gigantic. So the average, I would say, on the powder sold as is the red point here below August 2023. I realized there was somewhat big grains in the standard, so I crushed it, hoping it would get better results. So that's the data from September 2023. It's not really better, maybe slightly less variation, but still absolutely not a good standard. It varies from 5 to +20. And well, our average, I would say, are in agreement with what is published, but with an error bar of 13 per mil. Well, no kidding. Thankfully, overlap a little bit. So
you have another 5 minutes.
Okay, thanks. So what we noticed is in our study on samples from the Guatemala suture zone, we have 2 samples presented here that have very narrow range, in the range 2-3 per mil for boron isotopic signature. So we decided to analyze them both as bulwark and getting in situ data by SIMS to see if we get in good agreement. And so these are the data. So it's 2 chips of the same rocks that have been analyzed in situ by laser ablation. I'm still waiting for the SIMS data. It's a work in progress. And that are the bulwark data we obtained. And so what we can see is that we have much less variability than in the UBN standard. We vary, I would say, within 2 or 3 per mil. And at least for the sample on my right, serpentinites 1592, we have a good agreement with the published, bulwark data and the measurement by laser ablation. So I think the one on the left, well, it needs to be a little bit reworked, but we have lots of diopside vein that can probably make a problem, at least for the bulwark data. But for serpentinites 1592, except that data that is I would say, an artifact, we have a good homogeneous signature, and we overlap with bulwark measurement. So this one seems to be a good standard for in situ data as maximum effect, if there is maximum matrix effect, is in the range 2-3 per mil, which is which is the error we have on our measurements anyway. So this seems very promising as a standard. So this is what I just said. And so to conclude, we have seen that boron isotopes enables us to identify the source of fluid encountered in subduction zones. And so far, 2 major sources have been identified: seawater and subducted crust-derived fluid. And which is interesting is that both fluid can be present at great depth, well, the subducted crust, because it's where the fluid release happens. And at really great depth, you have the dehydration of the slab serpentinites that can release a very different kind of fluid. And so that has likely an impact in the arc magma formations. Okay, thank you very much for your attention.